I'm going to open the book, and I had the book here. It was just open, and now it's nowhere to be seen. So I'm going to close this, open the book again, right there, minimize the book again, and now open this back again. Where is it? I don't know why it does this. Okay, this is so aggravating. Here's what I'm going to do. I'm going to close that, and now try to open the book again. Okay. Okay. Let me try it one more time. It's just not opening. Maybe with that open in the background it'll work. Let's try that. Let me see if it's here. I don't think anything's there. This is so frustrating. I don't know why it will not open. There it is, right there in the background. And there we go. Showed up this time. Maybe I had to click on it. I don't know what the story is here. It's pretty frustrating. Okay, I think I'm going to move y'all to the top, and I'm going to move my taskbar. Yuck. Okay. Y'all can still see the book, right? Yay or nay? I hope you can. Can anyone see the book? Okay, good. All right. And then the next thing, well, we'll just start there. All right, goodness, that was way worse than it should have been. It seems like some more people may be waiting. Yeah, there they are. They never popped up, but here's Jemanuel and James too, right? Yeah, James and Jemanuel. Perfect attendance today again, folks. Way to go. Excellent. Guess what? Today has been a perfect attendance day. My Cal 2 was perfect attendance this morning. The Cal 3 finally was perfect attendance early this afternoon. And now y'all are perfect attendance. Way to go, folks. Okay. Sorry for two of you if you ever wait for a while, but your names never popped up out here. So I didn't see you. I just decided to check before we got started, and there you were. All right. Any questions on anything we've done up till now? All right. If not, we're in Chapter 2, which is first order differential equations. We've talked about the general case, which is sort of a lot of blah, blah, blah. And then we did separable equations, which are, to my mind, the easiest things to do. I think everybody agrees with that. Now we're going to do linear equations. Now, of course, linear equations is one of the classification things. They're either linear or nonlinear. But these are linear first order differential equations. This thing that we're doing now is not going to be for all linear equations, but only for first order linear equations. Okay? So we continue our quest for solutions for first order differential equations by examining linear equations. Now, linear differential equations are especially friendly type of differential equations in that given a linear equation, whether first order or higher order, there's always a good possibility we can find some sort of solution of the equation that we can examine. Okay? Remember last time we could come up with some integral defined equations you couldn't solve? Usually the linear ones you can. So here's the definition for the form of a linear first order differential equation given back in section 1.1, but this is when n is equal 1, first order. Okay? A first order differential equation of this form, a1 of x, remember that's your coefficient function that is only a function of x, no y's in it, only x. Because if there was a y in there, you'd have a y and the dy, and the same thing, can't have it. Plus a0 of x, okay, another function of x, coefficient function of x, times y. Again, you couldn't have any y dependence in the a here, otherwise that would be two y's in the same term. Can't have that. And that's equal to g of x. And generally, we only want x's on the right-hand side as well. So a1, a0, and g are all functions strictly of x, and then your first derivative and the function itself here. That is a linear equation, first order linear equation in the variable y. Okay? Now, that was the generic form. Okay? We sort of like to use what they call the standard form. And that standard form is dy dx plus p of x y is equal to f of x. Now, it's equivalent. All you've done here is divide every term up here by a1 of x. So here you're left with a coefficient of 1. Okay? Here, a0 of x divided by a1 of x, that's just a function of x. Let's just call it p of x. Okay? Just a function of x. And g of x divided by a1 of x, that would be f of x. Okay? So what we're going to do is start looking for solutions for this one, not for this form here. That's the generic form. This is our standard form. Okay? Now, before we start finding solutions, and this is a roundabout process, and it has you going in circles, kinda, literally, but before we do that, we seek a solution for this on an interval I for which both the coefficient functions p of x and f of x are continuous. So therefore, when we divided by a1 of x, we were making sure on this interval that you're interested in, none of those x's on that interval made this a1 of x 0. Because if it was, you can't do this anymore. So you have to restrict yourself to intervals where this is continuous and this is continuous. If you don't have that, these procedures won't work. Okay, now, before we examine a general procedure for solving this, note that in some instances, this can be solved by separation of variables, of course, okay? So here's one. dy dx, that's just like this one, equal 2x, that could be our p of x, times y is equal to f of x. Well, that's if that happens to be 0. Well, guess what? You could just write this in, subtract 2xy from both sides, okay? So you got dy dx is equal to negative 2xy. Write it in differential form. Dy is equal to negative 2xy dx. Then divide both sides by y. Dy over y is equal to negative 2x dx. That's separable. You certainly could do that. Okay? Now, This one, they've removed the y over here. All you have to do is subtract y from both sides. You have dy dx minus y, so your p of x is minus 1 times y is equal to 5. Well, that would be in this form, but written in this form, all you have to do is write it in differential form. Dy is equal to y plus 5 dx, and then divide both sides by y plus 5. Yeah, that's separable. So those are both linear and separable. But this one is not. Very simple equation. Dy dx equal to, the p of x is just 1. Really simple. Y is equal to x. No way you're going to separate those variables. That's not separable. So even though it's a very simple linear equation, you can't separate it. Okay? So we need a new method, because separation of variables will not work on this one. It would work on this one or that one, but it won't work on this one. Okay? So here's your method of the solution. Okay? Now, this method for solving that hinges on a remarkable fact, they say, that the left-hand side of the equation, let me go back and show you that equation. This equation right here in the standard form. This equation here, the left-hand side of that equation, can be recast in the form of an exact derivative. Not the way it is now, but by making one, finding what they call an integrating function, a special function of multiplying both sides of the equation. In fact, everything on each side of that, by that mu of x, you can make this, the left-hand side, be an exact derivative. And if it is derivative of a product, okay, then you can break it apart. And that's what we'll do. The problem is getting there, okay? And that's what you're going to do. This is what we're heading for. If we can make that d by dx of a product of u of x times y, okay? If you can find that mu of x, that's not a u, that's a mu of x times y, and make this a perfect exact derivative, then you can integrate both sides, okay? But here's what's going to be the requirement. If you're doing the derivative of a product, that would be the first mu times the root of the second plus the second y times the root of the first, okay? Now, rearrange that slightly, okay? And keep your mu dy of x, that dy by dx there, but break this down. Remember, oh boy, oh yeah, if you can come up with, that's where I was heading, that this mu is multiplied by both this and that, then you'll have it. So the requirement here is for this d mu dx to be equal to mu times that original p, the function p. Now, that equality is true. You can make that happen if d mu dx is equal to mu p. So, because that's what it is. So this is where we're going to be starting. If mu, you've got to find the mu so that d mu dx is equal to mu p. Now, that equation that we come up with can be separated. Write it in differential form. D mu is equal to mu p dx, because remember, p is a function of x alone. Okay, divide both sides by mu, and you have d mu over mu is equal to p of x dx. Okay, now if you integrate that, d mu equal p of x dx. That's what I just said when you divide both sides by mu, okay, and write it in differential form. This is true if log of mu, that's what the integral of this is equal to the integral of p of x dx plus some constant c. Now in a minute we're going to say, let's forget about the c, okay? But that's where we're heading. Now, is that someone sending a chat or someone trying to get back in the class? Oops, that's not what I wanted to do. I wanted to check and see if everybody's still here. We're still here. Okay. All right. Okay, sorry, I didn't mean to hit that. Quit popping up. Okay. I don't know if y'all can see that, but that is an aggravating thing that just keeps popping up there. All right. Now, that's what we want to happen. Integrate this, integrate that. Now, we just don't know if that is integrable. We are hoping it is. If it's a continuous function, it should be integrable. Now, that gives mu, if you solve for this, you exponentiate both sides, and if you exponentiate this, that becomes then a product. They're skipping some steps here. And I guess I need to put that step in. So let's go to our whiteboard and see if we can put that step in. Okay. Now, on the whiteboard, I think I'm going to move y'all back to the right and move this toolbar that you can't see out of my way. And then I'm going to scoot the whiteboard as far to the left and up that I can. Now you probably just see white. You don't see what I'm doing, but that gives me maximum writing space. Okay. Now, let me pick up where we left off before. Okay. Turn too many pages. Okay. Here's what we had. And hopefully it made sense. I'll start over a little bit. What we had gotten down to was d mu over mu is equal to p dx. Remember, p is a function of x alone, so this was a separable equation. Okay? Now, when you take the derivative of this, you integrate that. I said derivative, integrate both sides. What you have here is log mu, natural log of mu, okay, absolute value of mu, is equal to whatever that integrates as, p of x, I'll put the x in there, dx, and then you have an integration constant. Now I don't like them putting it there, but I'm going to do it. I would have put it as a log u, but log c, sorry. Okay, if you exponentiate both sides, exponentiate a log and you get mu. Okay, now they don't do absolute value anymore, but because that could be, so let's just do mu of x, remember it's a function of x alone, is equal to e to the integral of p of x dx plus c1. Okay, you're just exponentiating that whole side. But an exponent of a sum is the product of the exponents. So I'm going to put the c with that, so that would be e to the c1 times e to the integral of p of x dx. Okay, so that's where it's up. Well, this is just a constant. So what we have now is mu of x is equal to some constant, and they call it C2. Okay? C2, that's this thing right here, it becomes your C2. E to the integral of p of x dx. Okay, that's what your mu is. Okay, so you found your integrating thing. Okay, now it says, and here's where they hit weasel words. So I'm going to go back here and let you read this, but I've got you down. I showed you the steps they skipped. Probably were others that you probably wish I had shown, but I got to move y'all around. Jesus, you're in the way again. Okay, there you go. So what we've done, we've got this form right here. Mu of x equals C2 e to the integral of p of x dx. Now, it says even though there are an infinite number of choices of mu, they're all constant multiples of this thing right here. All produce the same result. Okay? Therefore, we can just choose our favorite C2, and they choose it to be 1. Please don't ever choose it to be 0, okay? 1 is a good choice. So now we've got mu of x is equal to e to the integral of p of x dx. Okay, time out. That's what we're looking for. That is our integrating factor. Okay, so what we're going to do, multiply both sides of the equation by that integrating factor. Okay, and that's going to make this thing right here a perfect derivative. E to the this thing, that's your mu, times dy dx, plus p of x times e to the blah blah blah, y, equals e to the blah blah blah, f of x. Okay? Now, let's take a look at this. Is that a perfect derivative? If it is, it's a perfect derivative of e to the blah 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 times y. Let's see if it is. That would be the first, there we have it, times the derivative of y, there we have it, plus the y, there we have it, times the derivative of this. Now, do we have that? Well, derivative of e to the blah 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 is e to the blah blah blah. And then chain rule has us taking derivative of the integral. Well, derivative of integral, that just undoes it, and that gives you, indeed, p of x. Okay? So sure enough, this is a perfect derivative of a product of your integrating factor times your original function y that you're looking for. Well, you still have this on this side, so what you can do is integrate both sides. Integrate a perfect derivative, you get that. Okay? Integrate this, and there's your answer. Okay. However, you need to solve for y, and this gets a little squirrely. So basically, we divide both sides by this thing here again. It's in the integral there. It's outside of the integral here. And they put it to the -1. That's the same as 1 over that. Okay? But it's also multiplied down here too. Now, the point is, don't try to memorize that formula. The procedure is what you follow, not the formula. Okay? I'm going to need to turn on the ceiling fan. This morning was quite cool in here. This afternoon it is beginning to warm up a little, so let me turn that on so I don't get quite as hot. So here is the procedure. And at first it seems really daunting, but it's not bad once you get to doing it a few times. It gets to be old hat. Put the equation in standard form. dy dx by itself, and whatever else you have is a p of x, times y is equal to whatever else you have out there, f of x. Get it in standard form. Then, from that standard form of the equation, identify that P of X. What is that P of X? The first thing you do to it is integrate it. Integrate that P of X dx. Now, if that's not integrable, you're in trouble, okay? But most of the time it is going to be integrable. So integrate it. Once you get it integrated, raise it as the exponent of P, the integral of it. That's just going to be some function, okay? Do e to that function, okay? You don't need a constant. Don't worry about putting a constant on that. Just integrate it and get the basic integral. Now, once you found that, that is your integrating factor. Whatever that is, e to the whatever that is, multiply that by everything on both sides of the equation, okay? And then you'll find that the left-hand side is a perfect derivative of the product of that e times y. I check it out every time. And then over here, you have that integral of e to the integral of px, whatever that function is, times your f of x. Integrate both sides of this, and that gives you this product here on this side. Whatever the function that comes up to here, hopefully it is integrable, and then divide by this, okay? Again, a lot of blah, blah, blah. So let's do it with this function here. Solve this linear equation. Okay, I think I'll go back to the whiteboard and we'll take this one step at a time, and after a while you'll see, hey, I got this. Just do it often enough so you do got it. Okay, I'm going to have to move your manual. He's in the way again. Okay, there we go. And we're going to clear the drawings from that one, and let's get, wasn't that example 1 at the bottom of the page? I believe it was, wasn't it? Yeah. And you see, you don't haul around integrals, you haul around what they integrate as. So this is going to be dy dx. Okay, that's starting well. Minus 3y is equal to 0. Okay, now first and foremost, that is separable. So we're going to come back and check and make sure we get the same answer no matter what we did. Okay, but we're going to do this one by our linear method. First thing, identify your P of X. Your P of X is minus 3. Carry the sign with it. So let's write that down. P of X is equal to minus 3. It's what's multiplied by y. Next thing we're going to do, integrate the P of X dx. Integrate this dx. And what you have is this integral of P of X dx. Really don't need to write that anymore, but I'm writing it now just so you'll see it, is equal to minus 3x. Okay, what do we do with that? We raise it as the exponent of e. That's what this thing is. That is your integrating factor mu, a function of x. Okay, what do we do with that then? We multiply everything on both sides of the equation by that. So you get e to the minus 3x dy dx is equal, no, I'm sorry, minus 3 e to the minus 3x times y is equal to 0, because e to the whatever times 0 is still 0. Now, hopefully, supposedly, this is a perfect derivative, d by dx, of, now what's it supposed to be? It's supposed to be the perfect derivative of your mu, which is e to the minus 3x, okay, times y. That's what we hope it is. Here is the point I go back and check and make sure. Derivative of a product is the first, which is e to the minus 3x, times derivative of the second, that's your dy dx, plus your second, y, times derivative of the first. So derivative of e to the minus 3x dx is going to be an e to the minus 3x times minus 3. So this plus is going to become a minus, and then I'm going to squeeze my 3 in there as well. Minus 3. So there is a product of that. Is that what we've got up here? E to the minus 3x, dy dx, minus 3, y e to the minus. Yes, it is. That's it exactly. Okay? So what do? We integrate both sides. Okay? This was just checking to make sure we did it right. We're going to integrate a perfect derivative and integrate 0. Okay? That's not going to be too bad. The integral of a perfect derivative is this product. E to the minus 3x times y is equal to, and the integral of 0 is some constant. So that's just going to be our arbitrary constant. And then what do? Multiply both sides of the equation by e to the 3x. So this goes to 1, so that gives you y is equal to c e to the 3x. There's your constant. You don't have a plus c, the c is incorporated there. Now, let's go back and do it separation of variables. That would be dy dx, I'm going to go and add it to both sides, is equal to 3y, because that was a 0 over there. Okay, I'm going to write that in differential form, dy, I'm going to go on and divide by y, okay, is equal, is equal to, Ryan must have gone out and come back in. Okay, hopefully he's back now. Okay, so I divided by y and write it in differential form. That would be 3 dx. Okay, divided by y and wrote that in differential form. This is log y is equal to 3x dx. Oh wait, okay, let's integrate both sides. That'll be 3x plus c. Now I'm going to write that as log c. That's still a constant, log c. Okay, now what I'm going to do now is exponentiate both sides, and that would be y is equal to e to the 3x, let's just leave that c for now. We'll call it c1, okay, plus c1. And just like we did before, an exponential of a sum is the product of the exponentials, and that's going to be e to the 3x times e to the c1. Well, let's just make that c. And there we have precisely the same answer. So yes, this method works. And guess what? You're not hauling around all those integrals. You're integrating them, okay? And once you integrate them, you're just hauling around that function, okay? And you're exponentiating that function, or whatever you're doing to it. It's simple. A lot simpler than that convoluted formula they were giving us. And that's why they said, don't try to follow the formula, okay? Do the procedure. And that's what we did. So let's go back and see how they did it. And I got to move Jesus out of the way again. In the way again, Jesus. Okay, here we go. Here's your formula. This linear equation can be solved by separation of variable. We already said it. Alternately, it is already in standard form. Your p of x is minus 3. Your f of x is 0. Okay? There's your p of x. So the integrating factor is the integral of that p of x, which would just be minus 3x. Don't use a constant with it. Then take that, raise it to the e, so the integrating factor will be e to the minus 3x. Okay? When you multiply that by everything on both sides, that gives you this thing equals 0. Now the thing is, notice that is a perfect derivative of your product of your integrating factor times y. Okay? Check this and see. That would be derivative of a product is the first, e to the minus 3x, there that is, times dy dx, there's that is. Plus, but hold off on the plus for a minute, derivative of this times y. Well, there's the y. So then what is the derivative of this? That would be e to the minus 3x times a minus 3. So there was your minus 3, e to the minus 3x. There's your y, and that's equal to 0. Integrate both sides. This is a perfect derivative, so that just comes out e to the minus 3xy is equal to some constant, because the integral of 0 is a constant. It's not 0, it's a constant. And then you divide both sides by e to the minus 3x, which is multiplying by e to the 3x, and there we have it. And that's good for all values of x. Okay? All right. Any questions on that? That's a simple problem, simple to do. We did it. Let's do the second one then, example 2. Any questions before we move to 2? Okay. What we're going to do for 2 is go back to our whiteboard and clear this. So I got to move your manual again. You're in the way again, your manual. There we go. And clear that. Clear all drawings. Okay. Now, example 2. Let me get my book in my lap so I can read it better. Here's the, dy dx minus 3y, is this looking sort of familiar? Is equal to 6. Okay. Now guess what? This one also is separable. Just add 3y to both sides, you get 3y plus 6. That's a function of y alone, and then you can proceed with there. But let's try it with our other technique, the linear technique. First thing is, identify your p of x. Okay, this is already in standard form. Coefficient of 1 here. There's your p of x. Now there's your f of x. So the p of x is that. So what do we do with p of x? We integrate it. So integrate minus 3 dx. And that's equal to minus 3x. Don't put a constant with it. Just leave it there. Minus 3x. Just like we got before. Okay? Now, what are we going to do with that? Raise it to the e. So this will then be our integrating factor. Mu is going to be e to the minus 3x. Just like it was before. But this time we're multiplying these out, just like we did before. E to the minus 3x dy dx minus e to the minus 3x, 3e to the minus 3x times y is equal to 6e to the minus 3x. See, we don't have a 0 there anymore, we have something else. Okay? Now, supposedly, this should be a perfect derivative of the product of our integrating factor, e to the minus 3x times y. So let's see if it is. That would be the first, e to the minus 3x times the root of the second, dy dx. That part checks, just like before, plus the second part here, y, times the derivative of this part, which would be a minus 3 times e to the minus 3x, and that's exactly what we got. But this time this is equal to 6e to the minus 3x. Okay? Now, writing that separable, so write it as a, well, no, we don't need to do that. Let's just integrate it. Integrate both sides. Okay? And this gives us e to the minus 3x times y, which is the integral of a perfect derivative is just what's inside. Okay? That's equal to, now, you might, oh, I forgot to put my dx here. Okay, now, if you want to, and it's not a bad idea, let's do a u substitution here. Let u equal minus 3x, the innermost part of the complicated part of that problem. Okay, then, okay, I've got a phone ringing, I don't have to ring. Du is equal to, take the derivative of that, minus 3 dx. Okay, that's done. Well, we had a 6 dx, so let's take the, all we want is a dx here, so let's divide by the minus 3. Okay, these go out. Okay, and then this will become minus, when you divide 6 by minus 3, you get a minus 2, and then the integral of, this will be the integral of e to the u du, because we took the over minus 3 out. Okay, and this would be minus 2 e to the u. Well, what is u? Minus 3x. Okay, now we want to know what y is, so multiply both sides of the equation by e to the 3x, and this will then be y is equal to minus 2. Is that? Oh wait, I forgot my plus c. And that does cloud the issue a little bit, I think. Plus, yeah, I'm sorry, minus 2 plus c e to the 3x. Yeah, that's where it goes, because you're multiplying both sides of the equation, both terms on both sides by that. That should be our solution. Let's see what we got. Minus 2 plus c e to the 3x. And that also, and by the way, you're always supposed to give the interval over which it's good. That's good from minus infinity is less than or equal to x, less than or equal to positive infinity. Okay, there's your interval. Now, let's go back up and see how separation of variable was on that one. Okay, let me do this in a different color. What color would you like me to use? I've got purple, red, pink, yellow, orange, 3 shades of green, and 3 shades of blue. Pick a color. Purple, red, pink, brown. I didn't say brown before. Yellow, orange, 3 shades of green, or 3 shades of blue.
3 shades of green.
Okay, which shade? Light, medium, let me see it. You got sort of a sage. Okay, pick a green. Purple, okay. It's actually more of a lavender. Okay, so let's do that. It'll be dy dx. What I'm going to do is add the 3y to both sides is equal to 3y plus 6. Okay, and then write that in differential form. Dy is equal to 3y plus 6 dx. Now I'm going to do something a little strange here. I'm going to pull out the y, and that'll be a dy is equal to y plus 2 times 3 dx. I just factored out the 3 and put it with the dx. Okay, now I'm going to divide both sides by y plus 2. So your dy over y plus 2 is equal to 3 dx. Separation of variables. Integrate both sides, and you get the log, natural log of absolute value y plus 2 is equal to 3x. Exponentiate both sides, and you get y plus 2, because when you exponentiate a log, they undo each other, is equal to e to the 3x. Now I think I forgot to do my plus c. Okay, I'll call it c1. Okay, we've been through that before. And this becomes y plus 2 is equal to e to the c is just some other constant c, e to the 3x, and then subtract 2 from both sides, and you get y is equal to minus 2 plus c e to the 3x. There you have it, minus 2 plus c e to the 3x. Either way gives it to you. Separation of variables, a little bit easier, fewer steps, but this one's not bad either. Okay? Now, let's go back to the text. And we'll watch what they did, see if they did it the same way. I'm pretty sure it's pretty close, at least the first part. They didn't do it. Got to move Ryan, he's in the way again. Okay, there we go. All right, here was your problem. Linear equation is already in standard form. The p of x is minus 3, just like before. The integrating factor then would be e to the minus 3x, because you integrate minus 3 and you get minus 3x. Raise it to the e, you get e to the minus 3x. This time multiplying the given equation gives you, because you still got something, you got something on this side now other than 0, the e to the minus 3x and dy dx here. Minus 3 times e to the minus 3x times y is equal to 6 e to the minus 3x, because we multiplied everything on both sides by e to the minus 3x. Now, the left-hand side, excuse me, I've been having a lot of congestion lately, so I think the changing weather has something to do with it. Probably fall pollen season has something to do with it. And the fact I did a bunch of yard work last weekend probably combines those together. All right. Okay. So when you multiply this, this is the same thing we got before. This is the product, derivative of a product, perfect derivative of a product, e to the 3x y, e to the minus 3x y. Take the derivative of c. First, times the derivative of the second, right there, plus the second, there's your y, times the derivative of the first. Derivative of e to the minus 3x would be e to the minus 3x times a minus 3, so there's your minus 3 e to the minus 3x times y. That is a perfect derivative, and that's equal to the right-hand side. If you integrate both sides, the integral of a perfect derivative just gives you what's inside, e to the minus 3x y. Integrate this, and they did the same thing I did, kinda, but they sort of do it differently. I wish I had kept the 3 inside here, taken a 2 on the outside. If I had had enough foresight, I would have done that. And then, but that gives us minus 2 e to the minus 3x plus your constant c when you did the integration. And then what you do is multiply both sides of the equation by e to the positive 3x to wipe out this one. It wipes out that one, and that just leaves you a minus 2 there, and then you have plus c e to the 3x, and there you have it. Now, that ends example 2. Now starts what they're going to talk about next. Okay? I won't do, okay. Okay, I guess, yeah. I think I will scroll down just a little bit further. When you deal with this solution, you have a whole family, depending on what c you choose. If you choose c equals 0, that gives you basically your equilibrium critical point value, y is equal to minus 2. There you have it. And when x is a very large negative number, this thing is going to 0, so you still have a minus 2. Okay? However, when x is getting to be a large negative number, this can be really taking off. Now, if c happened to be negative, it's going down this way. Positive going up this way. 0 staying right in the middle. Okay? And this is a family of curves. They didn't say what the values for the blue curves were, but one is C positive, one's negative, red C positive and negative, green C positive and negative, and yellow C positive and negative. Okay. Trying to see what in the world they're talking about next. Yeah, thought that was it. If you write this in normal form, which means this isn't linear, okay? It is a linear function, but we're not going to treat it linear anymore. We're going to write it as a normal function. Dy dx is equal to 3y plus 6, which is 3 times y plus 2. That's what they've written here. And then you look at that and say, there's your equilibrium position, y is equal to minus 2, because when this is 0, you have when y is equal to minus 2, that makes your dy dx 0. That's what I'm trying to say. And that's then called your critical value for y, which makes the derivative equal to 0. And that means, of course, the function is the closer it gets to minus 2, the flatter it is, it's going to 0 in the long haul. Now, the solution curve with the initial point, they haven't given us an initial point yet, so I don't know why they're saying that, either above or below the graph of the equilibrium solution, y is equal to minus 2, pushes away from that horizontal line as it increases. So that's what we mean, it becomes a repeller. Because this form, for larger and larger x's, this is blowing up big time, because e to any large number is going to be an incredibly large number, so you're getting further and further away from your equilibrium position, y is equal to minus 2. So, I don't know why they chose to throw that in now, but it certainly is true. That's fine. Throat is dry. One sort of problem with it is I was trying to cram down lunch, and today was the day our cleaning lady comes. She comes up every 2 weeks, and she's a talker. So I had gone outside with the dog so I could finish eating my lunch. Well, she wrapped it up inside and came out to chat for a while, so I wasn't able to really finish. I finished eating while she was talking, but I didn't get very much drunk, so therefore my throat is incredibly dry, so sorry about that. So anyway, here's your general solution. Again, suppose that the functions p and f in that original thing are continuous on some common interval I. Okay, in the steps leading up to our solution there, we showed that if the original equation has a solution on I, then it must be of the form given by that 4. Okay. Conversely, it's a straightforward exercise in differentiation to verify that any function of the form given in 4 is a solution of differential equation 2 on that interval I. In other words, 4 is a one-parameter family of solutions of equation 2, and every solution of 2 defined on that I is a member of that family. So therefore we call this the general solution. So let's go up here and remind ourselves what that 4 is. Okay, that's the one you weren't supposed to memorize. Oops, let's not go too far down. Okay, I need to go a little further. Why is that messing up? Going the wrong way is probably why. Okay, so this is the general form of the solution of 2, which was your, goodness, that's on a previous page. There, that form there. Okay, so that's what they're saying. That general solution that they said, do not memorize the solution. That's the general solution for any linear differential equation of the form of 2. Okay, now, why they're saying all this, I'm not really sure yet. Now, therefore, we call for the general solution of that differential equation, R. Okay, now by writing 2 in the normal form, y prime is equal to f of xy, we can identify your f of xy as minus p of x times y plus f of x, and the partial of f with respect to y is minus p of x, because that's the only y dependence you have there. And from the continuity of p and f on the interval I, we see that the capital F and its partial with respect to y also continuous on I. A lot of blah blah blahs here. With theorem 1.2.1, way back there as justification, we conclude there exists one and only one solution of this differential equation, with that as a boundary condition. Of course, with it doesn't have a boundary condition, infinite number of solutions, whatever C is. But with a boundary condition, you know that what you just calculated is going to be it. You don't have any spurious, convoluted, complicating issues there. Everything is on the up and up. Okay. Now, here's example 3. I think I'll go to the screen share, the whiteboard. Okay. Example 3. I haven't flipped my page over to page 58. Here we have it. Let's clear the drawings and move to manual. Okay, got it done. Goodness, my nose is itching. Must be going to have company, or we've already had company. Now, for some reason, my whiteboard shifted. So let me get it a little to the left, and we're fine up and down. Okay. Example 3, top of page 58. How about this one? Whoops. James must have had to go out and come back. Have we got everybody here now? 5. Yeah, we got them all. Okay. So here we have example 3. X. Whoa, I'm in blue. Lavender. Let's go back to black. Okay. X dy dx minus 4y is equal to x to the 6 e to the x. All right. Now, I'm going to make a prediction here. This is not going to be separable. Anyone want to debate that? I think that's probably going to be pretty clear. Not going to be able to separate those variables. So we don't have a fallback to say, oh yeah, this is the right answer because we got it this way. Well, we got the book. They'll tell us. But on the other hand, this is not in standard form, is it? Because with that value x there. So let's divide everything on both sides of the equation by x. Now, you might say to yourself, is that legal? Because x could be 0. Well, wait a minute. I don't believe x can be 0. Because if x were 0, if x were 0, then this wouldn't be a differential equation. This would be minus 4y is equal to 0. And that for y is equal to 0. Say that again. Okay, I still couldn't hear you. Would I mind doing what? Okay. Sorry, my hearing is bad and it wasn't coming in real strong. But you see, if x were 0, this wouldn't even be a differential equation. That would be 0 minus 4y is equal to 0. Okay, so y is equal to 0. So that's just a point, 0, 0, not a differential equation. So x can't be 0, obviously, so we can divide by x. Well, here the x's do go out. Here, one of the x's goes out, and we get down to x to the 5th. There. So let's rewrite this in standard form, and this would be dy dx minus 4 over x times y is equal to x to the 5th e to the x. Okay. Now, we really don't care right now for that x to the 5th e to the x. Who cares about that? We'll deal with that later. What we're interested in now is identifying your p of x. Here it is. The p of x here is minus 4 over x. And what are we going to do with that? Integrate it. So the integral of, I'm going to bring the minus 4 on the outside, and that just leaves me, and this is dx over x. Just integrate that. Well, that looks like that's minus 4 times the log absolute value of x. Okay? Now we know already x can't be 0. You can't take the log of 0. We've already covered that. That is your integrating factor. Oh, no, it's not quite. Not quite. Okay? Here's what we're going to do to it. My nose is itching. Okay? We're going to raise that to the e. Remember, that's the next step. But before we do that, let me use a rule of logarithm, and that says this is the same as the log of x to the minus 4 power. You take the coefficient in front and make it there. Now I really should have absolute value of x, But since it's a 1 over, or maybe I should still put it absolute value of x, because you can't take an even root. So let's do this. Let's just make that absolute value. Or one other, see if that's, I'd say let's leave that alone. Now let's take the e of both sides, or e. Raise that to the e, and the e and the log cancels each other out, so our integrating factor now is x to the minus 4. And I think we can lose the absolute value bars now. Just say x has to be positive. Otherwise you can't take the fourth, no, I'm sorry, not a fourth root. Sorry, I was thinking 1/4. X to the fourth, that's 1 over x to the fourth. X to the fourth is always positive. Okay, so I think we're okay there. Okay, so that's our integrating factor. So let's take that back to our standard form here and multiply the mu by that. So this will be x to the minus 4 dy dx minus, and here we have a 4, and you multiply x to the minus 4, that's in the denominator, so that's going to give us x to the 5th in the denominator, okay, times y, and that's equal to x to the minus 4 times x to the 5th is just x e to the x. Okay, I hope you followed all that, no sleights of hand there. Okay, now the question is, I think I do want to go back and write this, so let me erase this. I was contemplating it when I was writing it. Oh no, at some point in the day the eraser just stops working, and I don't know why. It's reached that point. Let's write this as minus 4x to the minus 5. Okay, so we won't have that in the denominator anymore. All your exponents are in the numerator, even though they're negative exponents. Okay, now supposedly this should be a perfect derivative of the product of your integrating factor, which is x to the minus 4 times y. Let's see if that's true. Product rule, first, x to the minus 4 times the root of the second. Sure enough, that's right. Plus the second, y, times the derivative of this. Well, the derivative of this will be minus 4x to the minus 5, and that's exactly what we got there. So that is a perfect derivative. That lets you know you've done your steps right, and that's equal to x e to the x. All right, if you integrate both sides of this, put a dx out here, this gives you x to the minus 4 times y. Over here, looks like we got to do an integration by parts. Let u equal x, dv equal e to the x dx. Okay, then du is equal to dx, very nice, and v is equal to e to the x, because the derivative of e to the x is e to the x. So that works out nicely. So what is our answer then to that? That would be u times v, which is x e to the x, minus the integral of the bottom line here, e to the x dx. Okay, which would be x to the minus 4th times y is equal to x e to the x minus, and what's the antiderivative of e to the x? E to the x plus c. Okay? And then what we're going to do is multiply both sides by x to the fourth, and that gives us y is equal to, multiplied by x to the fourth, this will be a x to the fifth e to the x minus x to the fourth e to the x plus c x to the fourth, sorry, x to the fourth. That looks like our solution. Let's see if we can find it here. Y is equal to x to the fifth e to the x minus x to the fourth e to the x plus c x to the fourth. Yeah, kind of ugly, but done. And my goodness, did that not bring us right up until 345? Okay, didn't plan it that way, but it did. Worked out all right. Let's go back to our book. Any questions on that before we leave the screen? Anybody? All right, then let's go back to the book and just find where we were there. Sure enough, there was our solution. Y is equal to x to the fifth e to the x minus x to the fourth e to the x plus c times x to the fourth. So we'll be beginning next time right here on that red arrow. And let me erase, if I can find my eraser here, my former mark on the page, so I don't get completely confused, just partially confused. And we'll pick up there on page 58. Now, homework exercises, this is sort of a long section, would be any of the odds 1 through 23. This is on page 62. That are in the back of the book. Do any of those you want. Any of the odds 25 to 35 that are in the back of the book. Any of them you want to. Okay, let's see. Let me not get too far ahead. No. Stop at 23. Any of the odds 1 through 23. Because 25 is initial value problems, and we haven't quite done those yet. I don't think you'd have any problem with them, but we'll wait and do those next time. So any of the odds 1 through 23, that's on page 62. Any questions? Okay. Now, 3 of you I'll see tomorrow, hopefully, in linear algebra class. The rest of you, all of you, have a good weekend. Of course, to make it a good weekend, several things are required. Work on some differential equations, and some of you some calculus and linear algebra too. Also, maybe your research papers, not a bad thing to do, but then to be safe. Folks, it's still going around. I just had one of my students, he going to the doctor tomorrow to see if he can get back on campus again. He's been his 2 weeks. He tested positive. He's had a very mild case, which is very fortunate, but he did have it. His roommate, they were keeping social distance, wearing masks. His roommate so far hasn't come down with any symptoms. That's a good point. However, one of my instructors, kid came home from school. They made him go to school. Came home from school asymptomatic, didn't know he had been exposed, didn't know he had it, gave it to his mom. His mom is was very, very sick. And the dad wasn't doing too well himself. I think he came through it okay. The mom hopefully is better now. It's a bear. It is a real bear. So folks, be careful. Be safe. A student in my other class, in my trig class, had a death of her grandmother, and all the family has come into town for the funeral, and a bunch of them are in her house. You know, her house is full. I said, please be safe. Please be careful, because it will get you. And it just loves, that virus loves weddings, funerals, any kind of celebration like that. Bachelor parties, I don't care what. It will spread around like crazy. One story my wife heard from Starbucks, I don't know where this was, somewhere, a guy came in who was asymptomatic, was not showing any symptoms at all, sat either in front of the vent that fed air to the whole store, or he sat right under the return that spread the air throughout the whole store. And the people in the store, the customers, were of course eating and drinking, so they didn't have their mask on. But every one of the, I think it was 4 employees, because they could talk through their mask, but they weren't eating and drinking, they had their mask on. None of them got sick. The majority of the people that were in the store got the disease, and several of them passed it to other people. So folks, be careful. All right, that's my paid political announcement. Any last thoughts, parting shots before we leave? Okay, I'm stopped sharing. So now I'll end the meeting for you all, so y'all have a good weekend. See 3 of you tomorrow, okay? Bye-bye.